Welcome to the Physics Files channel. We're all familiar with weather and how it affects our daily lives, but did you know that space weather also affects us? This video will give a straightforward description of space weather, which is driven by the sun, and it will be illustrated mainly by images taken by NASA's Solar Dynamics Observatory. So put on your sunglasses and get out your sunscreen. All that is coming up next. In the early 1800s, the orbit of the planet Mercury was not fully understood. German astronomer Heinrich Schwabe set out to study this by searching for an unknown planet inside of Mercury's orbit that could disturb it. The problem would not be resolved until Einstein applied his theory of general relativity, but Schwabe became interested in the pattern of sunspots that he observed on the sun's surface. This resulted in a long-term study, and in 1843, he published 17 years of observations showing the discovery of the sunspot cycle. Today, we know the number of sunspots as an indicator of the sun's magnetic activity level. The greater the number of sunspots, the greater the solar activity. Recorded sunspot cycles during the space era are shown in the figure. The amplitude of the cycle can vary substantially, while the recent time periods have been about 10 to 12 years long. Today, we're in the rising portion of a cycle, with activity increasing more rapidly than the prior cycle, but probably not as fast as the most active one shown. So what are sunspots? These are regions where the magnetic field structure of the sun has become tangled due to the sun's rotational motion. This inhibits convective transfer of heat, so the region is cooler and appears darker when viewed in visible light, as shown by the image on the left. The color of this image is similar to what would be seen on Earth. The yellow and sometimes reddish color of the sun results from the filtering of sunlight through the Earth's atmosphere. An image taken in extreme ultraviolet light at the same time is shown on the right. These images must be taken from space because extreme ultraviolet light is absorbed in the Earth's upper atmosphere before it reaches the ground. The bright areas are regions where large amounts of this high-energy radiation are given off. It is seen these active regions correspond closely to the sunspot pattern, indicating that sunspots are a good proxy for solar magnetic activity. Ultraviolet radiation is invisible to the eye, so the color of these images is false. This image and the ones taken by the Solar Dynamics Observatory are typically color-coded to indicate the wavelength of light that they were taken in. Let's take a closer look at these magnetically active regions. This video is a 5-day time-lapse during an active period. The sun is composed of plasma, an ionized gas, so it is not a solid structure. The equatorial region rotates at a faster rate than the polar regions, causing the magnetic field to become stressed and store potential energy in these active regions. Loops of magnetic field, called coronal loops, appear above the surface. The magnetic field itself is invisible, but the plasma spirals along the magnetic field lines and becomes visible as it glows. This video clip shows a closer profile of coronal loops rotating away over a period of about a day, indicating how dynamic the situation is. These active regions are often the source of events such as solar flares and coronal mass ejections that can impact the Earth. There's a tremendous amount of stored magnetic energy in the active regions. A steady stream of electromagnetic radiation is emitted from the sun's surface, ranging from low-energy radio waves to high-energy gamma rays, including visible light. Every now and then, a sudden burst of this radiation is given off. It's called a solar flare and is characterized by a sudden brightening of the surface, as you can see in the images. It travels at the speed of light and takes about 8 minutes to reach Earth. This can interfere with radio communications and high-frequency communications such as GPS. This video shows a succession of solar flare events from the same active region that spans a time period of about 4 hours. The type of event that is generally responsible for the major disturbances in the near-Earth region is a coronal mass ejection. Particles such as protons and electrons, in other words plasma, continuously stream outward from the sun's surface. This is called the solar wind. Once in a while, there's a large eruption that sends a cloud of plasma into space. As you can see, the particles must have sufficient energy to escape the sun's gravitational pull. Looping structures on the sun's surface, such as this filament, can also result in coronal mass ejections. To put things in perspective, the Earth is drawn to scale in this image relative to the sun. In fact, volume-wise, the sun is about 1.3 million times the size of the Earth. The filament of plasma is contained and held to the sun's surface by the sun's magnetic field. When the field becomes sufficiently weakened or broken, the plasma lifts off the surface, and a coronal mass ejection begins. Billions of metric tons of plasma are ejected at an average speed of 450 to 500 kilometers per second. It generally takes 2 to 3 days to reach Earth. The Earth's atmosphere and magnetic field provide substantial protection, so direct exposure of the population is not a concern. However, astronauts can receive significant exposure, and satellite operations can be disrupted due to effects on electronic systems. The atmosphere is also heated, which causes the orbits of satellites to decay. For an extreme coronal mass ejection, its interaction with the Earth's magnetic field can couple to a power grid on the ground and cause a power outage. Okay, now that we've recovered from that blackout, we're ready to define space weather. We've seen there are two types of radiations emitted by the sun. The first is electromagnetic radiation, or light. The continuous stream of light given off is referred to as the irradiance, and there are occasional bursts called solar flares. The second type of radiation is plasma, or ionized gas particles. The continuous stream of plasma given off is the solar wind, and there are occasional bursts called coronal mass ejections. Interaction of these bursts of radiation with the Earth's magnetic field causes magnetic storms. In this sense, space weather is analogous to Earth weather because there are periods of calm followed by an occasional storm. This leads to a concise definition of space weather. It is the daily conditions of the space radiation environment driven by the sun. It's interesting to note that space weather and Earth weather overlap in the sense that space weather is the condition in the upper atmosphere and above, while Earth weather is the condition in the upper atmosphere and below. So there you have it. Thanks for watching, and I'll see you next time.